Salutations, mini mathematicians! So happy you could join us today. We're going to be doing 7.2D. It's a pretty quick lesson. It's about features of graphs and interval notation. Hopefully you have that printout because we're going to be looking at a couple of different graphs, A through P, to be talking about what features they have. So our purpose is we're going to apply appropriate math vocabulary to graphs and use interval notation to describe and create graphs with given features. And then we're going to apply our knowledge of this vocab and features to graphs illustrating real world situations. So let's go ahead and get started. So taking a look here, we're going to be sorting graphs A through P into the groups below by writing the letter of the graph in the correct description. So let's talk about what these mean, and then you can pause the video and kind of go through those graphs and think about which graphs belong in each one. So function is increasing on the entire graph. So increasing means as x increases, y is also going to increase. It's kind of like a positive slope. Function has a minimum point, and let's make sure it's a minimum point. That means there's one point that's lower than all the rest. Function is constant for an extended amount of x values. Well, think about on a graph, if x, for an extended amount of x values, if that y value is constant, meaning it's not changing, what do you think that's going to look like? Function's increasing on some parts of the graph, decreasing on some parts of the graph, and constant for an extended amount of x values on some parts of the graph. So we're going to have a little bit of increasing, a little bit of decreasing, and constant. And for it to be constant for an extended amount of x values, it has to be very obvious. Continuing, graph is discrete. We've talked about what discrete means in previous modules. It means because of the context that the data points are not connected, so they just look like little dots. And then we can look at continuous, which is the opposite discrete, meaning all those data points are connected. Linear function, we've been talking about that quite a bit this module. Linear function means that the function has one constant slope, one constant rate of change. There's one line, an equation I can write for that. Nonlinear means a curve. So all of these functions are either going to be linear, nonlinear, or multiple linear functions on the same graph. So notice how we're going to be sorting them. So let's start with our function is increasing on the entire graph. So if we take a look, if we look at A, notice A is a linear function that's increasing on the entire graph. So I'm going to put A. B is increasing, but then it's not increasing or decreasing, so we're not going to pick B for increasing. Notice C goes up and then kind of comes down and then goes up. There's definitely a point of inflection. I wish I could zoom in on this paper for you, but just to look a little bit clearer, it kind of looks like this little Humpty Dumpty. It's a cubic, if you're wondering. Taking a look here, we're decreasing and then increasing, but remember, we're looking for something that's increasing on the entire graph. And these are all going to be functions, so we don't have any vertical line segments. Ooh, take a look at E. This follows this linear increasing pattern, even though data points aren't connected. Maybe for another one, discrete. But it's increasing the entire time, so we have A and E. F, notice it's down here. Sometimes it's hard to see these horizontal lines when they're on the paper. Sometimes I like to highlight the functions that I'm looking at so they really stand out to me. Let's take a look at our next one. If we take a look at G, G's decreasing and then increasing. It's a parabola, it's a quadratic, but not what we're looking for. H is a sad parabola. It looks a little wider too. So remember, we'd be multiplying by like a fraction there. But we're increasing. Oh, but then we're decreasing. Here we're decreasing, and then we're going to continue decreasing, just not as fast as we were before. J looks really similar to C. It's related. It's another cubic. You can really tell that we're increasing, oh, then we're decreasing, oh, then we're increasing. K is similar to that cubic, and it does kind of have this same squiggle. That's just a sideways squiggle. But it doesn't have any horizontal or vertical points. So it's going to be increasing. I guess this wouldn't be a function, though, if it was like that intense. So let me see if I can do a better job. Increasing, increasing, increasing. So K is always going to be increasing, and one reason we know it doesn't go back and decrease at all is because it has to be a function. So K is another one that we can put here for increasing on the entire graph. Let's take a look at L. L is a cosine. It increases, decreases, increases, decreases, increases, decreases. And you'll work with cosine in high school, really cool functions. Let's take a look at M. Oh, increasing and then still increasing. So M is increasing the entire time. N is decreasing, then constant, not increasing or decreasing, and then increasing. So it's not N. And O, it looks like one of those absolute value graphs. Decreasing and then increasing. And P, let's see, increasing, 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 and still increasing, all positive slopes. So we have, let's see, 1, 2, 3, 4, 5, A, E, K, M, P. I have another one on my answer key. Let's see. So A, E, K, M, and P. If you looked at C without it zoomed in, you may think that C was always increasing. So if you put C there, I'd take it just because the picture's not that great. But it's not. If we could zoom in, you would obviously see that it's not. So why don't you go through and sort the rest of these functions, and when you're, so pause me, and then when you're done, you can check back in and we'll go over the rest. Okay, let's see how you did. So functions that have a minimum point. Functions that have a minimum point, there's just one point that's going to be a minimum. I have B, D, E, G, and O. Not bingo was his name O. So if we take a look, B, there is one point that is a minimum. If we look at D, this 1 point to -5 is the lowest point on the entire graph. E, this is because it's discrete. This is the 1 point that's the lowest on the entire graph. And then G, this parabola has a minimum point. That vertex has the lowest point on the graph. And O, another discrete graph where that vertex is the lowest point on the graph. Notice for P, you might say P, but because this is still a continuous graph, we're not sure if it's going to keep continuing down or not, so we're not going to pick it. A lot of these graphs, you may say, oh, this is the lowest point, but notice that because these graphs, they're not just discrete, we can pretend that there's arrows on the end of all of them, and that shows us that these continuous graphs go on from -infinity to +infinity. So you can think about each x-axis going from -infinity to +infinity, and the same thing with the y-axis, -infinity to +infinity. And that's going to really help us be talking about how these functions grow. Okay, so function is constant for an extended amount of x values. So really what we're looking for there, you might have noticed, is a horizontal segment. And that's going to be B, F, and N. So again, you're just looking for those horizontal segments there. And looking at B, we have a constant. F, the entire function. And then if we look at N, we also have this horizontal segment. Our y value is not increasing or decreasing for an extended amount of x values. Okay, so functions increasing on some parts of the graph, decreasing on others, and is constant. that is only our friend n here. So the only one that decreases is constant and then increases again. And you can kind of sort them through since this is the only one that has constant. You can see that there's B, F, and N. Those are your only options you have for this one. Graph is discrete. Well, those are all the functions that have the data points not connected. So that's going to be B, E, and O. And continuous graphs, that's all the rest of them. So just sing the alphabet to yourself, but skip B, E, and O. Ready? A, C, D, F, G, H, I, J, K, L, M, N, P. Hope that was enjoyable for you. Keeping on going, linear function does not mean it has to be continuous. It can be a discrete linear function as long as it follows a linear pattern. So I have A, E, and F here. Nonlinear functions are curves. There's a lot of nonlinear functions here. C, G, H, I, J, K, L, M, B, N, O, D, P. And you can say that B, N, O, D, P, although those are not linear and they're not a curve, we can still consider them nonlinear functions if we're saying something's linear or nonlinear. But the best way to describe them are multiple linear functions on the same graph. Whenever we talk about a nonlinear function, we mostly talk about curves. That's the most appropriate way, the best way to communicate that. So multiple linear functions on the same graph, that's going to be your B, D, N, O, and P. So although we've described things as linear versus nonlinear, if we take a look at n, we can definitely say it's not linear. It's not linear. It doesn't have one constant slope. But technically nonlinear we say is a curve. So n is one of those special cases where we can call it a nonlinear function, and we can more specifically call it, to communicate clearly, multiple linear functions on the same graph. So now what we're going to do is we're going to, now that we've looked and sorted and seen these relationships, in vocabulary, we're going to define them. So you can always pause the video if you need to copy down a definition. So the first definition we're going to talk about is an increasing graph, kind of like A, E, K, M, and P. And those are values of y increase as x increases. So that means the y increases as you move from left to right across your graph. A decreasing graph is the opposite. The values of y are going to decrease as x increases. So as you move left to right along your graph, just like you read a book, your y's are going to decrease. Constant graph, the values of y are neither increasing nor decreasing. They're going to stay constant as x increases. And we noticed, like on graphs B, F, and N, that creates a horizontal line. Discrete graphs, this is situation or context dependent, and that means the data points are not connected, where continuous is the opposite, where the situation or context, it's still dependent on that, data points are connected. So discrete graph, if we're talking about the number of apples you're buying, that's going to be discrete because you're not going to buy a partial apple. But continuous, if we're talking about the number of pounds of apples you're going to buy, that's going to be continuous because I can't buy 1.5 pounds of apples without buying 2 pounds of apples. Sorry, I can't buy 2 pounds of apples without buying 1.5 pounds of apples. So it's a continuous graph. Minimum point is the lowest point, just one. If there's two that are the lowest, there's no lowest. It's the lowest point y value on the graph, and maximum point is the highest point y value on the graph. And again, it's the point, not points. There's no s here. Cool. Let's keep going. So what type of slope in a linear function represents an increasing graph and a decreasing graph and a constant graph? So taking a look here, it's sometimes helpful to draw a picture. So an increasing graph, if I had an increasing graph, I'm just going to draw a quick sketch of a coordinate plane. And I'm going to have an increasing graph. So we're connecting what type of slope. So for an increasing graph, there's going to be a positive slope. If I'm looking at a decreasing graph, well, a decreasing graph has a negative slope. And a constant graph, well, a constant graph is a horizontal line, and that has a zero slope. And some of you little smarties are like, what about an undefined slope? Well, that, my friend, is a vertical line, which isn't a function. So we'll keep going. So 9, 10, 11, and 12 are pretty creative freedom. There's many possible answers here, and you just have to make sure you get all of the features in your cute little graph. So draw an example of a function that increases on some parts of the graph, has a minimum point, and decreases on some other points of the graph. So I'll give you a couple different examples in different colors. So increases, minimum point, and decreases. So I'm going to, maybe I can have a discrete graph. Oops, that's not a function because it would be a vertical line segment. Increases, decreases. I'm going to stop there. I'm going to erase that point that makes this not a function. Hey, now it's a function. So I could have something discrete. So it's increasing, has a minimum point, and decreases on some other parts of the graph. If I'm not using a discrete graph, I might have to make it decrease then increase. So some type of parabola action. We'll have a minimum point. Number 10, draw an example of a function that decreases on some parts of the graph, is constant for an extended amount of x values on some parts of the graph. So I just need to have decreasing and constant. So I could make that discrete. I could make it continuous. I could have a curve and then a horizontal segment. So again, up to you. Just make sure that horizontal segment looks a little better horizontal. Mine looks a little tilted. Number 11, draw an example function that is discrete, so data points are not connected, increasing, and nonlinear. So remember nonlinear, here we can make that a curve or multiple linear functions. So we can, so discrete, so it has to not be connected, increasing and nonlinear. Guess we could always check a slope. So I said, let's see, over 1 up 2, 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 and make sure your slope is constant. Oh, wait, it said nonlinear. What am I doing? Nonlinear. So nonlinear, we can be a curve. We have to be increasing. So I'm going to go over 2, up 2. Then I'm going to go over 3, over 2, up 3, over 2, up maybe 6, just so I can really tell that that's going to be a curve. Or I could make it increasing, nonlinear, discrete. I could make some dots this way, then make some dots. So I kind of have a slope of 2, and then I have a slope of 1, so that's going to be increasing and nonlinear. Draw an example of a function that is continuous, decreasing, and linear. Well, for that, continuous, decreasing, and linear, we have to make a negative sloped line, decreasing line. Use the graph to complete the following. So now we're going to be getting into the cool interval notation. So taking a look at interval notation, it says use the graph to complete the following. For what x values is the graph increasing? So if I'm going to look for where the graph is increasing, it's increasing from here to here, but also from here to here. So when we're looking at intervals of increase, we always talk about the x values. We use those as our endpoints. So because this is a closed, it doesn't continue on from there. Sometimes for closed, a lot of teachers will use a closed bracket, meaning it's not continuing onward like this arrow, it continues. So if it's open, we would use a parenthesis. And you'll be using more specific interval notation next year. For this year, we're just going to be focusing on basic interval notation, and we're just going to be using the parenthesis. So for what x values is the graph increasing? Well, it's the interval from, it's between -6 and -8. So -7 to -2, we're increasing. And then a different interval, so I'm going to put it as a different parenthesis, is from 6 to infinity. And you might say, well, Mrs. Barr, that's positive infinity. I know it's positive infinity, but just like we're not saying +6, with infinity, if it's positive, we don't put a symbol in front, but when it's negative, we do. And it just kind of makes our communication with math a lot clearer and simpler. Okay, so let's say what x values is the graph decreasing. So now decreasing, well, it's decreasing from here to here. And you might have a graph that there's no intervals of decrease, and that's okay. It's okay not to have a decreasing graph. So here, -2, and this x value is 2, so -2 to 2. And then for what values is your graph constant? Well, this graph is constant from here to here. And so for those x values, it's from just 2 to 6. So notice what we have here is we can put this all together and the endpoints should be overlapping, -7 to -2, -2 to 2, 2 to 6, and 6 to infinity. And we can see that we're starting here at -7 and we end at positive infinity. So I feel really good about that. So let's continue working with our interval notation here. And we're going to start looking at drawing our own graphs. Draw a graph that's decreasing, constant, and then increasing. So here, we're going to draw our own graph, and then from your graph, you're going to state the intervals. So you're going to have very different graphs than mine, possibly. What's important is you want to make sure that wherever your graph's changing, your point of inflections from increasing to decreasing are constant and vice versa. You have to try to make sure that that's on an integer value of x to make this easier on yourself. So taking a look, I'm going to draw a graph that's decreasing, constant, and then increasing. So I'm going to I'll start at -4. Why not? I like -4. And we're going to be decreasing. So I'll just pick a value over here. I'm going to decrease all the way to here. And then it has to be constant. And remember, for constant, it should be an extended amount of x values. So I'm going to go all the way to 6. And then it needs to be increasing. Actually, I'm going to put an arrow here. I'm going to make that an arrow, but make it obvious that it's at -4. And I guess I'll go to 7. Cool. So this is my graph. It might look a little different than yours. So my intervals of decrease, I'm going to be coming from -infinity and going all the way to 2. The intervals of constant, I'm going to go from 2 to 6. And, ooh, it says infinitely increasing. Darn, I guess I have to put an arrow there. Okay. Infinitely increasing, I went from 6 to positive infinity, so I just have to put infinity. Cool. Really nice job. Careful with those directions. Infinitely increasing down here, really should have put it in there too. Okay, so let's take a look. We're going to state the x and y intercepts for each graph as ordered pairs. we're going to state the intervals of increase, decrease, and constant in our interval notation. So again, interval notation is just talking about the x endpoints and starting points. So x-intercept here, so this is the x-axis. Anywhere the graph's going to intercept the x-axis is an x-intercept. X-intercept, your y is 0. So thinking about that, we have 3, 0. Our y-intercept is anywhere where the graph crosses the y-axis, which in this case is just one time at 0, 3. Y-intercept, your x is 0. Interval of increase. So taking a look here, there's one interval of increase from here to here, and that's from 3 to positive infinity. We just put infinity. Interval of decrease, there is an interval where this graph is decreasing. It looks like it's from 2 to 3. And the last possible interval is interval constant, and that's going from -5 to 2. And then just double check your endpoints match. So we started over here, so -5 to 2, 2 to 3, and 3 to infinity. Nice, feel pretty good about it. So why don't you take a look at 16? 16, you might need to do a little bit of work possibly, but it looks like all the values are given to you. So go ahead and pause me and fill it in and we'll check in. Okay, so let's take it out a look. So x-intercept, this graph crosses the x-axis twice, here and here. So this x-intercept is given to me. It's 1/2, 0. But if I take a look, I mean this x-intercept is in between 2 and 3, but I don't know exactly what it is. So let's see what we can do. Well, we know that this line includes the points 2, -1, and 3, 1. So what I'm going to need to do is I'm going to first need to find the slope of that line so that I can use slope-intercept form, y equals mx plus b. So to find the slope of the line, change in y over change in x, and I'm using the points 3, 1, and 2, -1. I'm going to circle my y's. So 1, let's put that down. 1 minus 1 gets me 2. So then 3 minus 2, order is important for slope. 3 minus 2 is 1. So I know my slope of my line is 2. It's a positive increasing line, so I feel good about that. And then taking a look, I'm going to use one of these points in slope-intercept form to solve for my y-intercept because I wouldn't know if I extended this line what it would be. I know it should be negative though. So taking a look here, I'm going to use 3, 1 just so I don't have to deal with any negatives. 1 equals 2 times 3, all plus my b. 1 equals 6 plus b, and b is equal to -5. So I know that the equation of this line is y equals 2x minus 5. So if I wanted to find my x-intercept, your y is 0, I would just solve for x here. And I would get that my x is 5/2, which is 2.5, which is very reasonable. And I'm really happy I did that work to make sure it's 2.5 and not just guess. So my other x-intercept here is 2.5. I'm going to leave it as 5/2, 0. Y-intercepts, well, that's a little kinder because they gave me this nice little arrow and labeled it for me. Thank you. Intervals of increase. This is the fun stuff. So I'm increasing from here to here, which this is 2 and that's 3. So from 2 to 3. Interval of decrease, I'm decreasing from here to here. So that is -1 to 1. And interval constant, we have 2 of them, which is good because neither of these endpoints match up. So I was like, oh, I'm going to do something wrong. But it's because there's 2 intervals of constant. We go from -3 to -1. And then we go from 1 to 2. Awesome. So hopefully you learned a little bit about interval notation and the features of graphs. I know we do a really nice job communicating in class, so maybe you already had a lot of this vocab and we're just applying it now. So thanks, me mathematicians. Do your very best. Be nice to everyone. Video bar out.